Well, welcome again. We're going to have a look at some tutorial exercises for Chapter 2, Section 3. Again, you might like to have a go at these yourself before looking at the worked solutions. So we're going to have a look at questions 6, 7, 8, and then another one, 9, which is a bit longer. So a slightly generalized version of Bertrand's postulate says that for n bigger or equal to 6, there are at least 2 primes between n and 2n. So we're going to assume this here. We're going to use that fact, which is a fact, to prove that if you take the sum of 2 consecutive primes, then that must be bigger or equal to the next prime in line. That is, pk plus 2 is less or equal to pk plus 1. Here is the solution to this. So we're assuming that n is bigger or equal to 6 and that there are at least 2 primes between n and 2n. And we're going to prove that the sum of 2 consecutive primes is bigger or equal to the next prime in the list. So firstly, we just check it for some small cases. So 5 is less, so if you take 2 plus 3, the next prime is 5, and 5 is bigger or equal to 5. You take 3 plus 5, the next prime is 7, and 8 is bigger or equal to 7. 5 and 7 is 12, which is just bigger than the next prime, which is 11. So we may as well suppose then that pk is bigger than 5. Now, there exists at least 2 primes then between pk and 2pk. So I like to draw a little picture here. So I've got pk and pk and 2pk. And we know there are at least 2 primes between these two. So that means pk plus 2 has to be less than, there are at least 2 primes between here and here, then the next 2 primes must be between here and here. So pk plus 2 has to be strictly less than 2pk. Now I can write 2pk as pk plus pk, and then you can see that pk is less than pk plus 1, and that's it. That's all we needed to show. So the sum of 2 primes is bigger or equal to, well, in fact it's strictly bigger than, once we get past, strictly bigger than, once we get past 5, which was that case here where it actually, if you had equality, you get strict inequality here. Sum of any 2 primes is strictly bigger than the next prime in the list. Question 7 invites us to use Bertrand's postulate to prove that for m bigger than 2, and if you take m factorial and prime factorise it, then at least one of these powers up the top must be 1. At least one of these powers must be 1. This is a little bit more tricky. The hint is to write m as either 2k or 2k plus 1 and look at the interval between k and 2k. And of course then, once we've got that, immediately it follows that m factorial can never be a kth power for any k bigger or equal to 2, because in the prime factorisation there'll always be at least one single prime to the power 1, so therefore it can't be a kth power. So part B will follow instantly once we get part A. So the solution of that, this is what we're asked to prove. So we're given m, we write m factorial in its prime factorisation. We're asked to prove that at least one of these indices must be equal to 1. Now the result is true when m equals 2, so I'm going to then take my m and write it as either, m is either going to be even or odd. And then I'm going to, in either case, I'm going to consider the interval between k and 2k. Now we write down what Bertrand's postulate tells us for that. So there is a prime that lies between k and 2k, and it's got to be strictly between. So k is less than k plus 1, and that then is going to be less or equal to our prime p, and 2k is less than 2k plus 1. Now we can see then that if m is 2k or 2k plus 1, then our p is less than m, so that's immediate. And if our m is 2k, then that means our 2p, so if m is 2k, then 2p has to be bigger than my m. Now that's in the case when m is even. In the case when m is 2k plus 1, we can see from this that 2p is bigger or equal to double this one, 2k plus 2. 2k plus 2 is strictly bigger than 2k plus 1, and that's my m if m is 2k plus 1. So in either case, that gives me that 2p is bigger than m, and we saw also, of course, that p was less than m. So that means there is this prime where m is between p and 2p. That means then that when you take m factorial, then p can only divide m factorial exactly once. So we've constructed this p using the k. Okay, so that then shows that p only divides m factorial once, so m factorial then, one of these primes up here must have a power of occurring exactly once. And of course then we can conclude that if k is bigger or equal to 2, m factorial is never a kth power. Question 8 invites us to use Bertrand's postulate to prove that every integer bigger than 2, so given any integer bigger than 2, k, then there is a prime where k is between that prime and twice that prime. So given any integer k, there is a prime that k is between some prime and twice the prime, strictly. And it suggests you might look at k even and odd separately, which often happens in theory. So here's the solution to this problem. If k is even, they suggested we look at even and odd. If k is even, then there is a prime between k over 2 and k, because k is even, this is an integer. That means then immediately we get k is between p and 2p, which is what we wanted to show. If k is odd, then there is a prime that's between k minus 1 over 2, that'll now be an integer, and k minus 1, and k minus 1 is less than k. So we immediately have p is less than k. We just need to show that k is less than 2p. So if k is bigger or equal to 2p, now k is an odd, by assumption k was odd, so if k is bigger or equal to an even number, then it's got to be bigger or equal to the number 1 up from there, so k is bigger or equal to 2p plus 1. But then this is impossible, because rearranging this gives me k minus 1 over 2 is less than p. Sorry, if you rearrange it, k minus 1 over 2 is bigger or equal to p, but we had up here that k minus 1 over 2 is less than p, so that's a contradiction. So that means my k must be less than 2p, and that gets the result out. Question 9 is somewhat more involved, and it's connected back with one of the results we used in the proof of Bertrand's postulate, which I left as an exercise, and here it is. So we were asked, we made this assumption in the proof of the Bertrand's postulate. We assumed that the product of all the primes up to less or equal to n was less than 4 to the n minus 1. Well, here was a little proof of that. And we're going to prove it by induction. So we let p of n for each positive integer n denote this proposition, where p is a product over primes. For a fixed integer m, we're going to suppose that Pn is true whenever n is less than n plus 1. We're going to do a sort of version of induction on this one. So I'm assuming Pn is true for all n less than some number m plus 1. And then we're asked to prove a number of different statements here. We're asked to prove that the product of the primes between this m plus 1 and 2m plus 1 is less than this binomial coefficient. We're asked to prove that this binomial coefficient is less than 2 to the 2m. And we're going to conclude then that the product of the primes, p less than 2m plus 1, is less than 4m. And then putting all that together, we're going to then give an inductive proof that Pn is true for all n. So here is this is a harder problem. It's got a little star there, means it's a bit more difficult. So here is the proof of this result here. So firstly, we look at the binomial coefficients are fascinating things, and their prime divisors have lots of very interesting facts about them. So firstly, I just write down what we mean by the binomial coefficient, and this number then contains the wrong piece of paper here. Sorry, let me do this again properly. So this is the question that we had. So suppose the product is less than that. We suppose that P of n, this statement here is true for n less than or equal to m plus 1 with fixed m. Sorry, so here it is done a bit more neatly. So 2m plus 1 choose m, that's what it looks like. So this number contains as factors all the primes in the set m plus 2, m plus 3, and so on up to 2m plus 1, because all of the prime numbers in this set are going to be there in the numerator, and they won't be cancelled out by the denominator. So that means if all of the primes in this set are contained in the numerator, then the product of all of those primes between m plus 1 and 2m plus 1, this is going to be less than this thing. So this binomial coefficient is bigger or equal to that product. Now for the second one, little result on this, we were asked to prove that this thing was less than 2 to the 2m. So we just notice that 2m plus 1 choose m and 2m plus 1 choose m plus 1 are the same by the Pascal's triangle. It's symmetric. And so these numbers are the same, so this number is equal to 1/2 the sum of these two. And so I can take these two terms and I can just add in a whole lot of other terms, and this is going to be less than that. Now we know that the sum across any row of Pascal's triangle is the power of 2, so it's 2 to the 2m plus 1, and when we simplify we get 2 to the 2m. Now part C asked us to prove that the product of the primes is less than 4 to the 2m for p less than 2m plus 1. So we split this up into two bits given what we've done above. So we write this as the product of the primes up to m plus 1, and then the primes from m plus 2 up to 2m plus 1. Now this one, by our assumption, we've assumed that the result we're trying to prove is true for m. So 4, you replace the n with m plus 1, you get 4 to the m. And this one we've just proven earlier was less than 2 to the 2m by using parts A and B, and combining those together we get 4 to the 2m. Now finally, putting it all together, we've just shown them that if the statement is true for m plus 1, then it's true for 2m plus 1, and we know that p of 2 is true, and that the product of primes p less than 2m plus 1 is going to be the same as the product of primes p less than 2m, because 2m is not prime. And that means the statement being true for 2m plus 1 implies it's true for 2m. Well, now using these two now, we can now prove it's true for all n by induction. You just start off, if we have p of 2 is true, so if we put m equals 1 into this line, we get p of 3. Once it's true for an odd number, it's true for the next one, so that gives you P of 4. So for this one, if we put, once we've got 4, once we've got 3 here, I should say, we can then also get, putting them as 2 plus 1 to give me 3, and then 2 times 2 plus 1 gives me P of 5, so P of 3 implies P of 5, P of 5 implies P of 6, and so on. You get every integer by these implications here. So the result then is true by a kind of version of induction.